Welcome to lecture 7 of the wireless communication course. So last time we talked about diversity, which is a way to improve the error probability, so it improves the reliability of communication. Today we will see another technique which is complementary to this, which tries to improve the data rate, so it tries to improve the performance in another dimension. As an example of an analogy to what we do, just like last time, let me again draw a little cartoon. So suppose that you are a parent and you have two children. So the first child is dumb and the other child is smarty. And you have a pot of money that you need to distribute to each of them. And you need to decide how much money you will give for their education in order to maximize their salary. And you have three choices. You could give them each 1/2 of the money. You could give everything to dumb and nothing to smarty, or you could give nothing to dumb and everything to smarty. And each of these choices will have different implications. So let's suppose that when you give nothing to dumb, he will have 0 salary. When you give everything to dumb, he will have a salary, let's say, of 10. And when you give half to dumb, he will have a salary of 0.1. Now, for the other child, if you give everything to the smart one, he will make a salary, let's say, of 10,000. If you give nothing, he will have a salary of 100. And if you give half, he will have a salary of 1,000. Let's see, just as an example. The question is now, how should you, as parent, give the money? What is the best strategy? And you could think of different things, right? So one thing you could do is to be fair. So that means that you will take care of the weakest child, and then the obvious choice would be to do this. Right? You give everything to the dumb child to make sure that both of them are doing okay. But if you think in terms of the total salary that they will make, then obviously your best strategy would be this, to give everything to the smart one, because the smart one will make better use of the money that you give to have a better education and make more money. And this contrast between being fair and going for the total best performance will be somehow the topic of this lecture. So you can bear this in mind as we proceed. I realize I forgot to set my timer. Let me do that now. Hang on. Okay. So today's topics, they will be covered in chapter 9 of the book. It's also a good time to recap the concept of capacity, right, which you may remember as log 2 of 1 plus SNR, because we will use it a little bit today. And these are the suggested reading sections from this chapter. Today's learning outcomes, we will talk a lot about adaptive transmission, where you adapt the transmission scheme given the channel. We'll talk about the benefits and drawbacks. We will numerically solve rate adaptation and power adaptation, and also implement something called water filling, which is why we have this picture on the first slide. Last time we talked about diversity. We talked also about diversity gain and array gain. We saw that when we transmit the same thing over multiple independent channels, and then we do coherent combining or maximum ratio combining, which is, well, actually all of this thing, then the combined output will be the sum of the output SNR will be the sum of the input SNRs. And this allows you to approximate back or to get back the performance of the additive white Gaussian noise channel. So it allows you to go from this very bad, really fading channel all the way back to the additive white Gaussian noise channel by just having more diversity branches, which of course comes at a cost of either taking more time, using more bandwidth, or you need more antennas. So as I said, today we will focus on a complementary aspect where we don't want to boost so much the error performance, but we care mainly about maintaining a certain quality of service. So we want to maintain a certain bit error rate rather than minimize it, or maintain a certain data rate in the presence of fading. And we will see different strategies for doing this. We can either not adapt, where we just say, okay, we will use a certain constellation and a certain transmit power, and we just hope for the best. And in order to then meet your performance requirement that I highlighted here, we need to be prepared for the worst case of your channel. Right? So in order to meet the requirement all the time, we need to have a large margin. So we need to probably have a very large transmit power to make sure that we always meet our bit error rate or data rate requirement. On the other hand, we could also vary the power or modulation format and adapt it to the channel. In order to do this, the channel cannot change too quickly, so it should, we assume that it varies slowly, so we have a slow fading channel, which allows us to feed back the channel state information from the receiver to the transmitter. So the receiver knows the channel and then can adapt its modulation format and its power given the channel, and then the receiver will of course demodulate and detect the data. There are other ways of doing adaptation, but we only focus on power and modulation format here. We will start with some assumptions. They are not too strict, but it's good to make them explicit. We'll have a discrete time channel. Every time we use a channel, this corresponds to one symbol time, which is approximately 1 over the bandwidth. The channel varies slowly in time, so that channel state information can be fed back. Channel state information is often abbreviated with CSI. It's a good word to know. The channel is assumed to be stationary. This means that the distribution of the channel is constant. It doesn't change over time. So let's say we have exponential fading and with the same mean, and always it's like that. It's also ergodic. This means that over time we see all possible realizations of the channel. The noise is Gaussian with standard power spectral density. We can then compute the instantaneous SNR as the transmit power. So let's assume that we have a fixed transmit power times the channel gain. So actually I should mention, this is the power of the channel. So the channel, let's say, is called beta of k. And then G of k is equal to absolute value beta k squared. So this is the power of the channel. Right, so then the transmit power, the power of the channel over the noise power. So noise power spectral density times bandwidth. We can then compute the average of both sides. This leads to the average SNR, which then depends on the average channel gain. Right, and then the distribution of the SNR is denoted by P of gamma, and this distribution does not change over time because of the stationarity assumption. Right, so now we're faced with a channel that can change over time, slowly. We know the distribution, and then we also have access to the current channel, and we want to then optimize our transmission. As a benchmark, it's good to think how the performance will be when we don't adapt the transmission. In that case, we will consider the following case. We have a fixed bit error rate, a fixed transmit power, and a fixed modulation format. Okay, so this target bit error rate is the bit error rate that we want to maintain. For instance, let's say 10 to the minus 3. If it's 10 to the minus 3 or better, we're happy. Otherwise, we're in outage. Given the modulation format, we know the rate, right? It's the number of bits that we send every symbol duration. We can then compute the spectral efficiency also. And transmission takes only place when there's no outage, which means that when the SNR is high enough that the modulation can meet the requirement. So by this we mean the following. We have SNR, we have the symbol error rate as a function of SNR in dB. We have some kind of threshold, let's say 10 to the minus 3. This gives some threshold of the SNR. So when we're above this threshold, we are good. When we're below this threshold, we're in outage. So then we have a certain outage probability, which now, well, you've seen before in the previous lecture. So the outage probability is the probability that the SNR falls below the, well, I guess they call it gamma mod here, so I should call it the same thing. falls below this threshold value. And then the spectral efficiency is then just given by 1 minus the outage probability times the number of bits. Well, I can also add plus outage probability times 0, because when we're in outage, we send 0 bits. So this gives us this expression. This is what we get when we don't do any adaptation. So now let's start to adapt and then see if we can do better. We will consider 3 ways of doing adaptation. The first one is rate adaptation for fixed transmit power. The second one is power adaptation for fixed rate. And the last one is both adaptation of both transmit power and rate. And if I go back to my example from before, let me see, I think this second strategy corresponds to giving all the money to the dumb son. And strategy 3 corresponds to giving the money to the smart son. You will see how this works out. So the first case is rate adaptation. And this is something that makes sense. So I say it makes sense because power adaptation without rate adaptation does not make sense. For a fixed target bit error rate and a fixed transmit power, we will choose the constellation. So we have a certain SNR distribution, as before, with a certain mean gamma bar. Then we have also a set of modulation formats available. So for instance, here in the figure, we have QPSK, 8 PSK, up to 64 PSK. We have our target bit error rate, in this case 10 to the minus 3, and on the x-axis the SNR. Now for each of the modulation formats, we have a certain number of points. So QPSK has 4 points, 64 PSK has 64 points, and there are some SNR thresholds, right? So for, let's see, QPSK, there's a certain SNR threshold, which is approximately 10 dB. So this means if the SNR is below 10 dB, we don't transmit anything. It's above 10 dB, we can send QPSK. Of course, if it's above 15 dB, we should send 8 PSK. It doesn't make sense to send QPSK because QPSK would have a very low bit error rate, much lower than what we really want. So this means that for each of these regions on the x-axis, here for these SNRs we'll send QPSK, here we send 8 PSK, oh, let me use different color. Here we send 8 PSK, here we send, oh, is that correct? No, that's not correct, sorry. Is that correct? Yeah, that's correct. Here we send 16 PSK, here we send 32 PSK, and so forth. So we basically partition the SNR region into different parts, and then with each region we will send at a certain rate. So we can then compute the average rate, which is the sum over all possible constellations, and for each constellation we have a certain SNR region. So for instance, from 10 to 15 dB for QPSK, in which case log 2 m will be 2, because QPSK has 2 bits, and we just then sum over all of these regions. We still have an outage probability, which is a probability that we're below here 10 dB, and this is the outage probability, okay, given by this expression. And this at least will do much better than the strategy of no adaptation, just because we have many more degrees of freedom in terms of the constellation. Let's do one example, but let's do that after the break. So let's take a quick break and then come back with this example.